who was the first to discover this. So, I guess we'll go with Alina.
Can I bring my paper out?
Sure, I don't care.
Okay.
You don't even have to come up. But we just need to remind ourselves what we did last week. You can if you want.
Okay. So,
Hey, Liam.
we compared the...
Okay, sure you are. Sorry, go ahead.
We compared, so we made triangles out of, squares. So,
You had different sizes of squares, right?
different sizes of squares, yeah. So there's, 10 square, 12 square, 13 squares, as an
I
example.
lost that.
A 12 by 12.
And then we squared them because they're a square to find the area. And then we did the small plus medium area, and then we did the large area. And if the small area plus medium area is greater than the large area, then it's acute. And if they're equal, it's right. And if it's the small area plus the large area is smaller than the small area plus the median area is larger than the smaller than the large area, then it's obtuse.
Yeah.
And we also did inequalities, which is
Ooh, that wasn't even in the textbook. So hold on, back up. You did inequalities. That was a whole different inequality. So before you shift those, before you shift to that gear, just before you shift to that gear, was anyone else absent aside from Audrey? I forget, so please help me out. Okay, this will be our test, as if it makes sense to you. So we had a variety of squares that we cut out. We arranged them in different ways with the edges of the squares, 3 of them, lining up to make a triangle. Certain ones that we tried didn't work. We'll talk about that in a second. But of the ones that did work and leave us a triangle in the middle, what we discovered based off the areas of them as a... Go for it, try it. Yeah, I'm looking for where my cutout squares are, but they may have gotten recycled on Friday. Hold up, I have an idea. This can work really fast, but you have to give me 45 seconds. Counting does not help.
Because of the inequality theorem thing in the figure.
What's the inequality theorem?
It's these things. So B plus C plus D
This whole thing
has to
was
be
created
greater
by
than
Pythagoras.
A, and the side A plus B has to be
So, to remind us all, hey friends, it's easier on your actual desk, which is why we did not do this sort of thing online. But if we talk about distances that could be triangles, certain ones work and certain ones don't. We'll talk about the why in a second. But this is what we did last week, and we played with it to the point that, yes, it does line up, assuming that a certain thing is true. And this is what I'm scared that people will have forgotten, which is why we're doing it again. But we essentially found out this table of data, that table of data, that if the 2 smaller squares, or legs, I guess we could say, have areas that are greater than the third, we actually end up with an acute triangle, meaning all the angles are less than 90. So if I actually played with this until it worked, all my angles would be less than 90. On the flip side, when the smaller squares, or smaller legs, I guess we can say, compared to the bigger one, we get an obtuse, meaning one of the angles is bigger than 90, right? Got to be bigger than 90, not equal to, got to be bigger than. So then, that's not for you guys. We talked about the triangle inequality theorem. This is what you need to make sure you actually remember, and if you need to write it down again, it will put it deeper in your memory if you write it down again. You want to explain it?
I'm pretty sure I messed up, so I think you should explain it.
Okay, so in any triangle, And we could draw a picture of a really awkward triangle now if you want to kind of reinforce into your brain it's any triangle. If I have A, B, C, A plus B must be greater than C. C plus A must be greater than B. And C plus B, well, that's kind of dumb obvious here, must be greater than A. And that holds true. I could actually rearrange the lengths of A and B. And I could point A in. And now C is a lot smaller than it was, but still, A plus B has to be bigger than C. A plus C has to be bigger than B. B plus C has to be bigger than A. All three combinations of one leg plus another leg have to be larger than the other leg, the leg you haven't used. If you haven't inferred this, the sides of the triangle are called legs. There's three of them. Don't ask me why. Simon?
So that has to be true, but then...
Always and forever, period.
But then if you have to do the, then when you do the squares, they can be...
That's 100% a different rule. This is why I was scared about the two rules we were talking about. I should have ignored the squares activity till we talked about this. Or we should not have looked at the areas till we talked about this. Remember, this is my first year teaching math 8. This was a boo-boo. I probably did this backwards. Fair?
This is length of sides.
This is length of sides. Now, to then clear up the confusion, when we put squares on those sides, like literally make squares, so C is going to be slightly bigger than A is squared, and B is slightly bigger. This is the activity that then we were saying, oh, bigger than creates a... What kind of triangle is this? It's an obtuse triangle, right? There's an obtuse angle right here. So if we go back to the table that we've been working in, we know that to get an obtuse... Well, that's so many slides back. To get an obtuse triangle, my two smaller squares that we make are less than the sum of the third. So actually, that's because my third side there is so big. Here, and then we got off on a tangent talking about trigonometry.
Trigonometry's cool.
No,
Yeah, but...
no, you're not even gonna laugh at the joke. But we got off on a tangent talking about trigonometry. Anyone should laugh. It's you, Logan. Come on.
I thought you were pointing at Xander.
Tangent is a function in trigonometry. But tangent is also when you get off on a tangent. I think I might have half a laugh. Maybe half a laugh. Okay.
I just needed more of a...
So.
I think I just needed more of a sign.
I'm not okay. I'm debating on scrapping my plans and totally doing something different. So give me a minute to for. No. Now we're gonna talk about that in a second because we get really, really particular when legs turn into not legs.
Arms?
Let's talk about one thing, and then I'm jumping off the rails, and we're going to start the next lesson, and we may end up ahead. Who knows? Oh, this is a ruler. If anyone lost what looks like a binder insert ruler, this has been here since this morning. Thank you. I kind of thought it was a scrap of paper, and it had just stayed there. Angle, similarity. Please write this down. This, honest to God, is a very important rule. Excuse me. No, it is literally angle, like A dot if you want to, but you don't even have to put dots. Yes, although we're looping back to it to make sure you understand how important it is. According to the triangle sum theorem, every triangle has what, Audrey? Triangle sum theorem. It's also the poster that fell off the wall. Yeah. lame dad type joke. No matter how hot or cold it is outside, the sum of the angles in the triangle is always 180. So if we know two of the angles in a triangle, this third angle has to equal the other third angle. Has to. Because A is equal to A, B is equal to B, whatever you want to call them.
What?
Do you actually have a wait what, or do you zone out for a minute and now?
I was writing.
You're okay. We talked about this last week. That's all I'm asking. Do you actually have a wait what? Or did you just That's gross, by the way. There's so much on the floor that you're picking up right now. It's gross. So, angle similarity starts with the understanding that if we know in two triangles, two angles that are the same. Do we what? We know they're congruent because the symbols they use here. This, yeah, if you can't see the chalkboard, if you can't see the board, that would help. Green has to be equal to green. They both have a single tick mark. Blue has to be equal to blue. They both have a double tick mark. So therefore, purple has to be equal to purple because of triangle sum theorem, which theorems are proven. Theorems are like facts. So they have to have the same angle measures. What this tells us is the triangles have to be similar, which means what? What does similar mean?
They are the same shape, but maybe not. They're the same shape.
Same shape, different.
Size.
Yeah. Same shape, you're absolutely right, but they could still be congruent. Same shape, different size. Similar is not the same. Right? Yeah, that's totally. Or like orientation means nothing. Congruent shapes can be oriented completely differently. That lamp is congruent to that lamp. That lamp is still congruent to that lamp. That lamp is congruent to this lamp. That lamp is congruent to that lamp. It doesn't matter how we orient this. That lamp is congruent to that lamp, even though it's moving. Does it like orientation does not change that one thing is the same as the other. This lamp is the same no matter how I turn it. Now, if I somehow magically, like, and that would be sweet, go David Copperfield and just like, whoa, and the lamp like decreases in size, but it looks the same, it's now similar, because it's similar to what it was, but it's not the same. It changed size. So, I wish I was a magician. That would be sweet. So, if you can shrink things down, this, I got another word for you, is called a dilation. Stop. I'm trying to listen and write, and it doesn't work. Have you ever been to the eye doctor? You've probably had this done. When they put the drops in your eye in a real dark room, it dilates your pupils, meaning they get bigger, and therefore can receive more light. But also, the doctor can look into your eye. Right? That's another reason why they dilate your pupils, is to get a better view of what's going on in there and check the health of everything. They also sometimes take pictures, which is really cool.
And they can be dilated if you're like high or drunk, I think.
So actually what's going on there is your eyes don't behave like they're supposed to, because the motor cortices, which is the plural of cortexes, don't fire like they're supposed to. So if your brain is impaired, also if you have a concussion or some other, like, they will flash a flashlight at your eye because it should quickly change size. Yeah, so like when Ike got his concussion, right, they probably either already knew, yeah, he's probably concussed, or if they're wondering, they do that because if your eye responds like it should, that's better. You still might be hurt, but like your brain is still firing like it should. If it doesn't, or it's really, really delayed, you know something's going on. Yeah, something's going on.
When I had a concussion, like, I decided to be in a dark room all the time because like the light hurt.
Right, because your eyes couldn't dilate like they were supposed to, so the light hurt you because your eyes weren't shrinking down to block it out. It was letting it all in.
The first time I had a concussion, I was really happy because the power went out, so I could go walk around and talk to my family.
Oh yeah, because the power was out.
Yeah.
Simon. I'm not sure. That's beyond what I understand. So this is going to be me being very me and hope that we can all make like an agreement. But if not, we can do this. My thought is we don't need to do this because what it's going to push you to do is square 5, square 6, square 7, compare the sum of 5 and 6 squared with 7 squared, and then do the same thing we did on the data sheet from Friday. Right? Like, would this be obtuse? Would it be acute? I don't think we need to do that.
Why do we need to square them?
Because that was how we could tell, are they acute or obtuse without actually building the triangle. Now, if you don't want to square the sides and be able to tell, will they be acute or obtuse? You can make the triangles. So my resources are your resources. So if you ever want to play with making triangles, these are a great way. Now, they only go so short, though, unless you connect onto here. So if I connect onto here, I can go as short as I want for blue. So if I make blue 5 and red 6 and yellow 7, it's a triangle. Well, when you connect it. But it doesn't work when it's super short. So this is going to get messed up. But we could look at, okay, is it going to be acute or obtuse? Like that sort of thing. And we can prove it by going back to the rules that we have from our data sheet. So like, let's do one real quick. What's 5 squared?
25.
25. Oh, come on. Come back. 25. 25, 36, 49. So when we sum the shorter legs, 61, how's that compare to 49? Greater than. What type of triangle was that? Acute, according to our data sheet. Sorry, I'm really distracted from the radio. I can't even write the word acute.
Why do you have that?
Because I'm like the 7th grade radio connection. Okay, if you want the like really real answer, in case an emergency happens, I'm pretty level-headed. So like a school lockdown or something like that. So please don't joke about like, oh, I'll take your radio. It's the reason I have it is not a reason that I wish was a reason. You know what I mean? If something bad goes down, that's why we have radios. So also so I can like bug the custodian when you guys spill stuff and everything. If we apply those rules, we could actually get those squares back out from last week. I don't know if any of you kept them, but like we could look at the all acute angles. Now, one of you is bringing up why are we squaring the sides and like why does this even matter? It doesn't really, except for one really, really cool situation. If we imagine back to last week of our 3 square, our 4 square, and our 5 square, I actually on your graph paper, draw a triangle. That now you can dilate this double or triple if you want, but go 4 tall, 3 wide, making a right angle here, and then make squares off of each of them.
Doesn't matter how big.
No, you can dilate it if you want. Oh, come on, smart. I'm just trying to paste a graph. Not 45. What type of triangle has a 90-degree angle and then 2 45-degree angles?
Triangle? Oh, right triangle.
Keep going. Even more detailed than that.
Wait, what was it?
Okay, apparently that's not going to paste.
A
isosceles, because if it has two 45-degree angles, two equal angles is isosceles.
Does that mean every right triangle is isosceles?
No! Please stop shouting out rules that are nowhere close to true. Sorry, that wasn't directed toward you. That was me. Like, we got to that point of you asking that from me trying to say no to somebody else asking another one of those things. So, on these triangles, any of these could be made, but they'd kind of be a pain in the butt. Like, when you go to arrange the squares, right? Like I was doing with the squares at the very, very beginning where we were catching Audrey up. It's kind of like I have to keep scooching and keep scooching and keep scooching. But in the situation that I want to create a right angle, there was a mathematician who figured out a really cool relationship anytime he forced this angle to be right. And where this is so amazing to see is even on paper that has specific squares, this line doesn't have specific squares. It's diagonal. So I could make up some weird name for that diagonal length, or, and this is what a lot of people did back then, take a straight edge, figure out how long that is, and transfer it somewhere else. So if I were to rotate that around here, and I didn't do it perfectly there, it actually, same line, that is this length. And this mathematician was like, huh, okay.
Pythagoras?
Yes. He's like, well, that's a nice number. It's 5. And beyond that being a nice number, when I did that thing that my math teacher had me do with this square and that square, actually, funny enough, this square has the same amount in it. Because this has 16, this has 9, and this has 25. So then he started playing with more. And he was like, all right, so wait, what if I do like 2, right? And he like made a little square off the side of it. Give me a length for down here.
9.
I heard 9. 1, 2, 3, 4, 5, 6, 7, 8. Oh, I was almost there. 2 and 9. So he's like, all right, I've got a 2 edge and a 9 edge. And then he took his straight edge and then he flipped it over to the actual graph that it works. Well, what's 2 squared?
4.
What's 9 squared?
81.
What's the sum of those?
85.
And he measured this and he's like, it's the square root of 85, which is a horribly gross number. But that's what it is. Because a squared plus b squared equals c squared is what he discovered. Right? That mathematician was, of course, Pythagoras. Well, I mean, you can argue that a lot of people that did things like that were doing math. So, where the heck are we? So many resource pages.
Yay! 9.2.
6, 8, and 10. Pythagoras quickly realized, and I'm going to jump through these things with you. Well, 6, 8, 10, how does that relate to our 3, 4, 5, Simon?
6. No, go ahead there. No. 3 multiplied by 2 equals 6. 4 multiplied by 2 equals 8. 5 multiplied by 10. 5 multiplied by 2 equals 10. Okay, there. Dilation.
It is a dilation. Now the question is, what about B? Sure, you guys have all heard about Pythagorean's theorem, and you've all probably even potentially used it before. Ooh, wait a minute. That's not 3, 4, 5, or 6, 8, 10, or crap. So like B, if we had squares with areas, and I know I got people only half with me because I feel like we need to speed up again, which we will after Discovery Day. For those of you who are actually with me, thank you very much. I do appreciate that. What would be the length of the side of a square with area 64? Charlie? Yeah, sorry, I was just kind of asking these to the class. But yeah, 8, right? 8, because it's a square. Don't argue, wait, we can do that differently. It's a square. What about 100? 10, and then 144?
8 squared plus 6 squared.
So, wait. 8, 10, and... On your paper, draw 8 and 10 if you have space.
Just an 8 by 8 square.
8 by 10, like the right angle 8 by 10. So, like, if I go, like, it's never funny. 1, 2, 3, 4, 5, 6, 7, darn. 8.
8 by 10?
Yep.
That's what he said. I'm so good at geometry.
Short by 1 again. So, let's come back from Pythagoras. So, time travel back to Friday, right? You're doing that little lab, and you hear from across the room a group go, oh yeah, 8, 10, 12, it's a right triangle. I wonder. Because in your true middle school fashion, you like to immediately try to judge what people say and like tell them when they're wrong and be like, well, actually. So, what would be your argument for is 8, 10, 12? I mean, 6, 8, 10. Right, hold on. 6, 8, 10. This did work, right? We said it does work because Simon told us, well, Simon and Bear, that it's a scale factor from 3, 4, 5. Right? So we had 3, 4, 5. It checked out. We made it. 6, 8, 10. Simon said it's just a double dilate. So it looks like, well, plus 1, plus 1, plus 2, plus 2. Right? So if we're just trying to make rules, Pythagoras, right? He's testing things out. If I add 1 and then add 1, it works. If I add 2 and then add 2, it works.
Well, then
So-
it works 'cause 4, 5, 10.
So then he tests out 8, 10, 12, question mark.
I missed it.
Patrick?
8 squared plus 10 squared would have to equal 12 squared, and it doesn't.
It doesn't.
It doesn't lie.
So this, he said, well, no, actually, that can't be 12. Would it be more than 12 or less than 12? If we say we have to make this a right angle, more than 12? Why? I don't know why there are like lots of people talking at the same time. Patrick, how did you decide more than 12?
Because a squared plus b squared is 164, and c squared is 144.
Yeah.
Since c squared is less, you have to make the c bigger.
Ah, so since this is 164 compared to 144, what we actually know is, well, this is bigger than that. Well, if these have to be equal, if we make it true, well, then this can't be 144. It has to be 164, which is really, really close to what perfect square? What's the next perfect square after 144?
16.
169 is 13 squared. 13 squared is 169. So we're almost there. This is almost 13. But we know it has to be greater than 12. It's almost 13. We know it has to be, if this is going to be true. Now, I'm not telling you you have to remember any of this. We're going to come back together and talk about it again tomorrow. But I just wanted to give you a little intro of where Pythagorean's theorem came from. I'm waiting for people to call me to schedule a door install, so I'll take that as a good point to end class.
What other things do you do?
What other things?
What other
Oh, a whole lot of things. You can look them up. Hello?
Pythagoras is probably cool. I'm pretty sure. I'm not sure about Pythagoras. Charlemagne. Charlemagne is probably great. He is Charlemagne. Andy Winter.
I have a no name 912. Charlie, come here. Put your name on the front one.
I'm gonna start